So you can basically use any online graphing website. One of them is math3d.org. Let us add an object. Here you have z equals to, so I'm going to use an explicit surface. So it gives you something. I'm going to change this and actually build my own surface. So x squared minus y squared divided by the sub function divided by x squared plus y squared. So this is the surface that we have. The function is continuous everywhere except for the origin. And a graphing app for you. So here you have your surface, this is your function, and as you can see, you have a better visualization here. This is the surface, and it's continuous everywhere except for the origin. Very well. Projection in xy plane, projection in xz plane, projection in yz plane. And if you just rotate this, you get your surface, which is here. As you can see, you don't have continuity at the origin. So we say that the function f of x and y is continuous everywhere except for the origin. So very well. You say that since 0 and 0 is not in the domain of the function, we are not able to discuss continuity. The first condition is not met, so remember that. Note that. Since the first condition, what's the first condition? The point must be in the domain of the function. So since the first condition is not met, the function is not continuous at the origin. Now I expect you to ask, what if I define the function at 0 and 0? Remember that in elementary calculus, they had something that we called removable discontinuity, and then jump discontinuity. They had different types of discontinuity. Here we are actually almost doing the same thing. We're trying to see if we can remove the discontinuity for this function. So let us move on to the next example. Question says, now suppose I just define the function at 0 and 0. Check this example. Let, instead of f, define g, function g and x and y to be, so you're defining a piecewise defined function. The first piece is x squared minus y squared divided by x squared plus y squared. If x and y is not at the origin, 0 and 0. And you say that, okay, I'm going to define the function at 0 and 0. Let's see. If x and y is equal to 0 and 0, I'm going to define the function to be 0. This is the z value that I'm defining my function with. How about this function? Is this continuous? Is this function continuous at the origin? Well, you have to check 3 conditions, one by one. The first condition says, hey, that point A and B, which in this case 0 and 0, is in the domain of the function. So what's the domain of this function? The domain is equal to. So the domain of the first piece of the function is r squared, your plane, minus the origin, and at the same time, you're adding the origin to the function g, and we say that, hey, at origin, you get the z value, which is 0. Union with 0 and 0. So what's the meaning of that? You're trying to fill that hole in the surface, and it is equal to r squared, the whole plane. So it means that the first condition is met. 0 and 0 belongs to the domain of the function. It means that 0 and 0 is in D. Okay, we're happy about first condition. Let us move on to the second condition. How about the limit? 2. The second condition, we know that the limit must exist when x and y, this point, any nearby point approaches to 0 and 0. Does it exist? Okay. Remember that when we have a function like g of x and y, which is defined this way, nearby points to 0 and 0 has definition x squared minus y squared divided by x squared plus y squared. To analyze the limit of the function, we use a general path. This is not a nice function. We have to be careful about 0 and 0. So to check the existence of the limit of x squared minus y squared divided by x squared plus y squared, we use a general path. A general path. What's the point? The point is to simplify this function, get rid of one of the variables, and make it to a nice function with only one variable. It makes it easier for us to analyze this function. One path, remember that we have different choices, many choices. General path can be of the form y equals to mx, y equals to mx squared, y equals to mx cubed. It can be y equals to square root of mx. Any path that passes through the origin. Remember that we are working with the origin. Or it can be x equals to my, x equals to my squared. As long as this path passes through the origin, we're good. Again, remember that if we use a different point like A and B, they have to change these paths so they pass through A and B. So my goal is to simplify this function. Okay, I'm going to use y equals to mx. The limit of x squared minus mx squared divided by x squared plus mx squared, while x, we don't have any y left. Yx goes to 0, can be simplified into the limit of x squared. Factoring out x squared, I get 1 minus m squared divided by x squared, 1 plus m squared. And x goes to 0. Of course, I can get the common factors, and as you can see, unfortunately, it depends on m. The limit depends on m, so it doesn't exist. Okay. The second condition is not met. So we cannot go further to the third condition. Since the second condition is not met, the limit doesn't exist, so the function is not continuous at 0 and 0. Since the limit does not exist, this function is not continuous at the origin. Very well. Suppose we have a function with 3 free variables. How about that? How do we analyze continuity of that function? First of all, it's going to follow the same process when you have a function in 3 free variables and you're checking the continuity at a point A, B, C. First of all, that point must be in the domain of the function. The limit must exist. Goes to A, B, C. So I'm just changing these, A, B, C. And let me just add Z here, A, B, C. So it must be in the domain of the function, the limit exists, and the limit of the function must be equal to the value of the function after you substitute that point into the function. For example, evaluate the limit of this function, x squared sine y divided by z squared plus 4 y x, y and z is getting closer and closer to 2, pi over 2 and 0. What's the limit of this function? And is this continuous at this point? Is the function continuous at 2, pi halves and 0? Okay, perfect. Let's take a look at this function. What do we have? We have an expression on the numerator, which is x squared times sine y. X squared is just a nice term. Sine is a trig function, nice function. On the denominator, you have z squared plus 4. What's the domain of this function? Note that the domain, always check the domain of the function. If this point belongs to the domain of the function, try to substitute that, see if the limit exists or not. Then go through choosing a general path and try to simplify the function. So the domain of this function, guys, remember that here you have x, you have y, and you have z, it means that the domain of the function is part of the space. The domain of this function is R Cartesian product with R, Cartesian product with R. It means that you have R cubed, the space. What's the meaning of that? It means that you are allowed to plug in any number you like for x, y, and z. On the denominator, you have z squared plus 4, which is never 0. Let me write the note for you here. Z squared plus 4 is never 0. If I plug in 0, it's 4. If I plug in 2, it's 8. If I plug in negative 2, it's 8. So it's never 0. And it's always positive. Z squared plus 4 is always greater than 0. So you can plug in any number you like for x squared. Sine y is a trig function, nice function, continuous everywhere. Z squared plus 4 is always positive. So we don't have anything to worry about here. The domain of this function is the space itself. You can plug in any point x, y, and z for this function. Very well. To find the domain of the function, we just investigate each of these separately. This is our domain. Now, let us evaluate the limit of this function. Remember that when it comes to limit, our very first step is to plug in these values. If we have a constant L, a number, it means that we're lucky. So the limit of this function, let us plug in 2 for x and y for sine y. So here you have pi halves divided by our z is 0, 0 squared plus 4, which is 4 times 1 divided by 4 equals to 1. This is the limit of your function. This is our limit L. Okay, is the function continuous at 2, pi halves, and 0? This point is in the domain of the function. 1, 2, pi over 2, and 0 is in the domain of the function. 2. We found the limit at this point. Limit of the function, we found it. It's just 1. At 2, pi over 2, and 0 is equal to 1. We're happy about that. Last condition, the limit of the function must be equal to the value of the function after we substitute them. 3, we know that the limit, which is x squared sine y divided by z squared plus 4, while x, y, and z approaches 2, pi over 2, and 0 is equal to 1. Is this equal to the value of the function at 2, pi over 2, and 0? Of course, we found the limit by substituting these numbers into the function for x, y, and z. This is equal to 1. It means that the last condition is met, so for sure you can say that the function is continuous at this point. So since all 3 conditions are met, we have continuity at this point, which is 2, pi over 2, and 0. This is your conclusion.